Hi class. In this section we're going to take a look at the factors that affect relative humidity. And if we just look at relative humidity as a mathematical equation, so relative humidity is the mixing ratio divided by the saturation mixing ratio. Okay, how do we affect relative humidity? Okay, here's relative humidity. We can either change the numerator or we can change the denominator. Okay, those are the two ways that you can influence or affect relative humidity. Well, the numerator is the actual amount of water vapor in the air. So one way we can affect relative humidity is by adding or removing water vapor. Okay, so let's finish off our title here. So factors that affect relative humidity, and that includes adding or removing water vapor from the air. Okay. All right, so let's go through an example here, and we're going to increase the amount of water vapor in the air. So let's make a table out of this. So let's start off with temperature in one column. And the next column will be the mixing ratio, the actual amount of water vapor in the air. And in the next column we'll have the saturation mixing ratio. So remember, saturation mixing ratio is the amount of water vapor the air could hold when it's saturated. Okay. And last column we'll calculate the relative humidity. So we will look at how relative humidity changes by adding or removing water vapor from the air. In this particular case, we'll be adding water vapor to the air. So let's start off with a temperature of 25 degrees Celsius. And in this particular example, we're just going to keep the temperature of the air constant. Okay. We'll start off with 3.5 grams of water vapor per kilogram of air. Okay, that's the actual amount of water vapor in the air. The saturation mixing ratio, remember, is dependent on the temperature. Okay, how much water vapor can the air hold if the air temperature is 25 degrees C? Well, get our saturation mixing ratio table out. At 25 degrees Celsius, the air can hold a maximum of 20 grams of water vapor per kilogram of air. Okay. So our saturation mixing ratio at 25 grams per kilogram is 25 degrees Celsius, sorry, is 20 grams per kilogram. Okay. So our relative humidity is the mixing ratio divided by the saturation mixing ratio. So that's 3.5 grams of water vapor per kilogram of air. It's always important to keep our units as they should be. Never forget to put units on. Relative humidity is mixing ratio divided by saturation mixing ratio, so 3.5 grams per kilogram divided by 20 grams per kilogram. So in this particular example, our relative humidity is 0.175, or 17.5% relative humidity. Okay. Alrighty, so now let's keep temperature the same, and let's increase the amount of water vapor in the air. Okay, so our temperature is going to remain at 25 degrees Celsius. Let's increase the amount of water vapor in the air to 7 grams of water vapor per kilogram of air. Since we kept the temperature constant, that means that our saturation mixing ratio is going to be constant. So once again, just remind ourselves at 25 degrees Celsius, the air can hold a maximum of 20 grams of water vapor per kilogram of air. So that stays the same. 20 grams per kilogram. And so our our relative humidity is the mixing ratio, 7 grams per kilogram, divided by saturation mixing ratio, 20 grams per kilogram. So this gives us 0.35 or 35% relative humidity. So by increasing the amount of water vapor in the air, we've increased the relative humidity. Of course, we've kept our temperature constant too. That helps to know too. Alrighty, let's keep going. All right, let's keep the air temperature at 25 degrees C. Let's increase the amount of water vapor in the air to 14 grams per kilogram. Okay. If our temperature stays the same, then our saturation mixing ratio stays the same at 20 grams per kilogram. And now our relative humidity will be mixing ratio, 14 grams per kilogram, divided by 20 grams per kilogram. So by increasing the amount of water vapor in the air, we've increased the relative humidity this time up to 0.7, okay, or 70%. All right, let's go one more time. So let's keep the temperature constant, 25 degrees C. Let's increase the amount of water vapor in the air to 21 grams per kilogram. Okay, we kept the temperature the same, so the saturation mixing ratio is going to stay the same. The amount of water vapor the air can hold when it's saturated, 20 grams per kilogram. So our relative humidity will be 21 grams of water vapor per kilogram of air divided by the saturation mixing ratio. The air could hold as much as 20 grams per kilogram. Okay, so this gives us 1.05 or 105%. Okay. But there is a problem here. Okay, relative humidity cannot be greater than 100%. Okay, so this greater than sign with a line through it, relative humidity cannot be greater than 100%. Okay, so in this particular case, the relative humidity equals 100%. And the air is saturated. Okay. Here it's super saturated, and we can't have that in natural conditions. In the lab, you can force that to happen. But in natural conditions in the atmosphere, we can't go higher than 100%. Okay, so the relative humidity is 100%, but notice we've got 21 grams of water vapor per kilogram of air actually in the air, but the air can only hold 20, okay? And so what happens with that extra 1 gram of water vapor per kilogram of air? Okay, so the relative humidity is 100%, and 1 gram of water vapor per kilogram of air, okay, condenses into, and in meteorological terms, if you're on the ground and this happens, you're going to form dew on the grass. Okay? Or if you're up in the atmosphere and this happens, you're going to form a cloud droplet. Okay. So in our particular example here, the factors that affect relative humidity, we added water vapor to the air, which increased the relative humidity of the air. Okay, again, we kept our temperature the same. Okay, and in our particular example, we did that until we reached saturation, and anything beyond saturation is going to condense out into a water droplet, okay? Either dew or a cloud droplet or, whatever, all right? So that's one of the factors that influence relative humidity. The next thing we'll take a look at is the denominator in this particular case, all right? That's coming up.